Hi, everybody. Welcome back to our Astro Bookshelf hangout that we do on most Thursdays here on Deep Astronomy. My name's Tony Darnell. I run this place. And today we are talking with Dr. Brian Keating, as we generally do, about what his goings on are on his channel. He gives us previews of some really great interviews that he has. In particular, this one we're going to be talking about is an interview he had with Dr. Sean M. Carroll, who is one of my personal heroes, and I loved watching his interview, and it was really very interesting. I would invite you, because the purpose of these hangouts is to let you guys, my audience, know about what's going on his channel, because there's a lot of overlap there, and I want to highlight what he's doing there. So by all means, click on the link downstairs in the description box to watch the full interview, but do it after we're done, because you want to hear what we have to say first, and we'll give you a nice introduction and everything to get you set up and ready to go for that discussion. So before I bring Brian up, I got a couple of announcements to make here on the Deep Astronomy World Headquarters. If you have, and I don't know why you would, but if you do have an Alexa Dot or an Alexa smart speaker thingy in your house, then Space Fan News is available to you now. Posted weekly. I have what do they call that? A flash briefing that I'm posting every Monday of Space Fan News, space headlines. And you could tune it in by just saying, "Hey, Alexa, what's my flash briefing?" And then you get to search somehow auditorily and pick Space Fan News. But the easiest way to do it that I found is just get on the Alexa app and do a search for Space Fan News and add it to your flash briefing, and it will come up every time you say, "Hey man," not "Hey man," but you gotta say, "Hey Alexa, do this." Now, I know that's weird coming from me that I'm on Alexa right now, or at least Space Fan News is, because I have a massive distrust of these things, anything with a microphone in my house. However, I got one. I don't know how I got it. I think somebody gave it to us and we set it up, and the sound was actually pretty good. I play Spotify on mine a lot, and I found out about these things, and I wanted to find out how to do it. The computer geek in me made me want to figure it out. So every week I'll be posting something on Alexa for you to watch or to listen to. Okay. So let me go ahead and bring up my co-host, Hort. Hey, Brian, you're on. Are you there? What are you doing?
Yeah, I am typing in that I have had an Alexa Ring. I bought one of those Alexa Loops, I think they were called.
Oh, yeah?
I did a review of it, an unboxing on my channel over the summer.
Oh.
And I got a lot of hate mail for that, but that's okay. People were saying, because I put out a security flaw in it, that it can basically read, someone can just find it and pick it up and start hearing your email, finding out what kind of pills you're buying on Amazon, what kind of products you might not want people to know about. So it can tell them your whole shopping list. And so I did a review that it is not ready for prime time. So look for that in my videos over the summer. But it's a serious security flaw, in my opinion. So yes, you're right to beware. But I do have a lot of Alexas. Alexa, play. What was it called?
This one's a Dot. It's like the cheapest thing you can get.
But what's the name of your show?
It's called Space Fan News. Space Fan News headlines, and it's really cool because I try to be like NPR, and I say, from deepastronomy.com, here is Space Fan News. And I'm Tony Darnell. And
Alexa, play Space Fan News.
Wait,
hold on. Alexa, play Space Fan News.
You got to do it at the flash briefing.
To intervene in the voting in 2 swing states.
So you got NPR.
Alexa, stop.
Want to extend the time for
Alexa, stop. For the love of Zeus. Please stop running my life. I mean, I basically bought everything. I bought the green screen behind me, my computer monitor stand, et cetera, et cetera. So they already know what colored pills I'm buying.
Yeah. And I'm sure you can order all kinds of stuff from your account too when somebody gets your thing. Yeah. Anyway, I did it because I wanted to know how hard it was to do. And it's really not that bad. You set up an XML file that's public. You set up you record an MP3 file that's also public. And I put mine on an S3 bucket and I'm done, and I just filled out the thing. And so that's how I did it. I might do a couple skills. I might do one that's like, what's up tonight, and then have it say what the bright things are up tonight. Like if you look in the south west or something, Mars is the bright red dot, and there's another bright dot that's Jupiter. Something very general that most people would want, not something in depth like, M31 is way over here, and if you have a 6-inch telescope, it's going to look like this.
It's all about the smudges. It's all about the dots and smudges.
That's right. So I don't know. I might do that if this.
That's a cool idea.
Yeah. So anyway, I'm doing that.
You can get Into the Impossible podcast, by the way. You can listen to the latest episode of the Into the Impossible podcast on
so
Alexa.
So I wonder if I can get Space Fan or Space Junk podcast on.
Yeah, you can. I think it probably automatically gets uploaded if you're on Stitcher or whatever. Yeah.
I am on Stitcher. So
or at least it should go up.
Oh, okay, cool. Well, I'll have to test that out then. See if we can get it on Alexa. I don't know how many people watching this have this smart crap. They call it smart speakers and all this. I personally, it's scary to me. I don't like microphones directly linked to Jeff Bezos in my house. But
the only place I have it besides behind me here in the studio is in my bathroom. And I figure, if they want to hear and analyze whatever big bangs,
man, that's brave.
whatever big bangs and dark matter is being produced.
Oh man, that's a little TMI, man. Wow, you're broadcasting that. Hey Jeff, take this, man. Guess what I had for lunch today?
No. It's not. I don't use the camera in the bathroom. Turn off the camera.
Oh, that's crazy. All right, so Brian, getting to the subject here. You talked with one of the people I love to listen to on his Mindscape podcast, Dr. Sean Carroll. And he's talking about all kinds of weird stuff in your interview. So for those of you who are checking in for the first time, why don't you introduce what you're doing over on your neck of the woods and what you talked to Sean about. And did you by any chance have any clips this time, or are we just going to talk about it?
If you want to, if you want to go to the video while I'm talking, you could probably mute it and show it, right? Just from my YouTube channel.
I could maybe try that.
Yeah, if you want to screen share, I'll talk about it. So here's what happened. So in 1997, I was a graduate student at Brown University, and one day across the early version of the New York Times webpage, I saw the universe is all screwed up, and here's evidence for the twisted universe, so to speak. And I was really quite amused and shocked and also excited, because the claim was that astronomers had detected a directionality in space, which sounds like, okay, there's a lot of directions in space. There's the direction of the sun, the galactic center, the black hole, and Sagittarius A star. There's all sorts of things that seem to prefer certain reference frames in the universe, including, as I had studied for a long time, the CMB dipole, which reflects the fact that the Earth is a planet riding in a solar system around a galaxy, which is moving with respect to the rest frame of the cosmic microwave background photons. And that, you might think, would define an axis in the universe. It turns out it doesn't necessarily do so in the way that would violate one of the most cherished traditions in all of physics, laws, some say. And that's called Lorentz invariance violation, LIV for short.
It's a crime in some states.
That's right. You have to obey the law, as Einstein would say. It's one of the underpinnings of all of modern physics. So actually, if you go to my blog, if you go to briankeating.com right now, I'll walk people through, Tony, how to get the slides that Sean and I reviewed in our podcast together. So if you go to briankeating.com, click on blog, you will be, first of all, you should all subscribe to my newsletter, because I have a lot of fun things coming up, including my new book, which I'll be talking about in future episodes with Tony, no doubt. I'm going to write a book.
Look at this thing.
Yeah, so pop up there. Sign up for the Twisted Universe newsletter. I
have to make me bigger, because they're looking at some tiny version of me. Okay, there we go.
Great.
All right, go.
So click up to where it says blog.
Oh, okay.
And you click on that. I go down, contact Brian. Go to Sean Carroll, the yellow lettering there. You should be able to click on that. Right there. Yeah. And then scroll down, and that should be number 7, I think, right there. Stop. Go back up. It should say download a PDF. So click on that, Tony. And download for free Sean Carroll. There you go. So everyone go through this. Please do sign up for my newsletter. And you should be able to open this or save it or what have you. And what was announced back in 1997 really startled me. And it also must have sent a thrill up Sean Carroll's leg, because Sean had predicted an effect back in 1990 when he was a beginning graduate student at Harvard University with George Field and Roman Jakiv, an effect that would lead to the very same observations that were made. And if you stop there, if you go right there, so this is what precipitated the conversation this past week. There was a claim produced on Physical Review Letters, which is the most prestigious, highest impact pure physics journal in the world. Nature has higher impact, but anyway, Physical Review Letters is for the most urgent, the most important news items, newsworthy, so not news, but actual research articles. So there was a abstract printed. They didn't print the whole paper. The paper is not available on the archive, but it said that there was extraction of cosmic birefringence from Planck 2018 data. And they show there this beta, which is a parameter that shows how much the universe is twisted in a certain sense that I can discuss. And they said they detected it with a significance that exceeded 2.4 sigma, which corresponds, as Tony knows, to a confidence of 99.2%. In other words, there's only a 0.8% chance, statistically speaking, formally, of this arising by chance. Now, I don't know about you, but I'd enter a lot of lotteries, especially one that would pay out with a golden medallion bequeathed in Stockholm. If I had enter a lot of lotteries that gave me a 99% chance of winning. So this was quite startling. And if confirmed, and as the authors say, there still needs to be research done. But Sean's theory would somehow be ratified. So my prediction is, if this were confirmed, that Sean would probably win the Nobel Prize for coming up with the theory behind it. And so if you go down to the next slide, Tony, you'll see that this paper came out on Galileo's birthday in 1990, on the 426th birthday of Galileo. And it was fitting that happens, because Lorentz violation is sort of a special case of what's called Galilean relativity, which is that the laws of physics don't depend on your reference frame. And what Lorentz violation means is that they would depend on your reference frame. There would be some reference frames are more special than others. And what Sean showed in the subsequent slide is that you could actually change Maxwell's equation. There's good old James Clerk. And you could modify the electromagnetic Lagrangian, that script L there, which is that's the Rosetta Stone, or as Sean Carroll, as Eric Weinstein often describes it, it's kind of like the force field, the governing entity, the Rosetta Stone of all physics is encoded in what's called Lorentz, the Lagrangian. And by adding this term, it's possible, a special term called the Chern-Simons term, which has a connection to my patron, my friend Jim Simons, that the result would be that physics would acquire a Lorentz violating, or perhaps parity violating, and Lorentz violating phenomena. And that's what Sean predicted.
Okay, so let's just review what you just said, because I'm a little bit lost. You started by saying the universe does not have a preferred direction.
That's Lorentz's. I didn't say that. Lorentz said that.
Well, okay, but that was the thing. Now, first of all, I don't know what you mean by a direction. Do you mean, because we live in a three-dimensional space plus time, we have X, Y, and Z coordinates with a direction and time. What do we mean by a direction?
So
does the universe always look in a certain area? That just doesn't, first of all, make sense to me, that statement.
Yeah, so it doesn't make sense because it's totally out of context with your normal experience. In other words, if you drop a ball and look at it and the Earth's gravitational field, it looks the same as if you observe that same ball after bouncing off the light bouncing off a mirror. In other words, it obeys certain symmetry laws, such that if you do a test of the force of gravity inside your laboratory, and then you move to from Florida to California, you should get the same results. And all conservation of momentum shouldn't depend on where you do the experiment. It shouldn't depend on what reference frame you're in. And what this is saying, if this were true, is that you'd get a different answer if you did it in a laboratory in Florida versus a laboratory in California. It would depend on where you are in the universe. So imagine if there is found to be a universal electric field. Imagine that there's a constant electric field, and it points from the constellation Andromeda to the constellation Delphius. Well, that would have certain types of behaviors. You'd get different behaviors of particles, of forces, of fields, depending on how your experiment was oriented with respect to that electric field.
Okay. And so to violate Lorentz, one has to have a preferred direction upon which your results of an experiment depend.
Yes, it could be a preferred direction or a preferred position. So you could, in the case I just gave, it gave a dependence on which state we're in, and but it could also be which direction you're looking in. So there's 3 spatial coordinates. There's three angles that specify where something takes place, or 2 angles specify it on the 2-sphere, and then there's a dimension of time, which could say you could also violate this, and that could be time dependent, as is sort of related to the claim that's being made in this paper.
Okay, so using your gravity analogy in Florida versus California, if this were being violated, if there were a preferred direction to gravity in the universe, then if I drop a ball in Florida, it will fall at a certain rate with certain vectors that are consistent with my being in Florida. However, I move to California and do that experiment. Something is different because of the fact that I'm in Florida. Maybe the speed is different. Maybe the X direction is a little off or something like that. Am I visualizing this right?
Yes, that's exactly right.
Okay.
So you'd be able to tell where you are in the universe. That's the thing. That's the key, is that you would have something.
Right.
Yeah.
Okay, so I would know that I'm in California based on how that ball fell.
Exactly.
Because there's a characteristic behavior of gravity at this location.
Exactly.
Okay, and that's what you mean by reference frame. It could also apply to my velocity somewhere as well. Exactly. I could be going different speeds or doing this in an airplane and getting something. Okay. Wow. And so Sean predicted that the universe.
Sean explored the consequences of a universe if this effect were present.
Okay.
And he actually tested it and set limits on the maximum amount of Lorentz violation and parity violation that could take place if the universe had this additional component that we don't believe, we know for certain isn't present in the so-called standard model of physics, which is gravity and quantum mechanics, particle physics, etc.
And so if it did have a preferred direction, the universe, then we would be able to notice it in this, what'd you call it? The some kind of polarization?
Yeah, so in this case, if you go down, the next slide after that, this kind of sets the stage. So if we stop here, now you and I have been talking about theories of everything ever since we were born. But for those that might not know, we've done a bunch of specials on theories of everything with some physicists that have their own theories of everything, including Eric Weinstein and folks like Max Tegmark. We did that over the summer. And I'm even going to have a second conversation with Sir Roger Penrose. He just agreed. It's funny. I sent him congratulations the day he won the Nobel Prize, and yesterday he answered me. Thank you.
Well, you're busy.
I said, yeah, I didn't expect to hear from you, but now that I've got you, do you mind coming on the Into the Impossible podcast for a live stream with my audience to take questions and answers in the next couple of weeks? And he said, absolutely. So look forward to that. Please subscribe to my channel, everybody, Dr. Brian Keating. And they download the Into the Impossible podcast as well. So anyway, so here's a slide from my friend Matt Muse up at Cal State San Luis Obispo. And he's showing kind of the way that physicists think about things, these blocks that my kids like to put together and break apart. The idea is that if there is a theory of everything, it's supported by these 3 pillars, namely that gravity is a manifestation of curved space-time. Lorentz symmetry is sort of the conjecture that laws of physics don't depend on position, rotation, et cetera, velocity. They can depend on acceleration because that now impacts curved space-time, but we'll leave that alone. And then quantum mechanics, the law of Schrodinger's equation, Dirac equation, those all support the standard model of particle physics on the left. and support general relativity, the two of those together. And then on top of that comes further downstream comes electromagnetism, chemistry, astrophysics, Newtonian gravity, etc. So next slide, please, Tony. I'm going to call you Newtonian, Tony.
New Tony.
Now, if you have a slight breakdown in the exact symmetry of Lorentz invariance, then you might see effects downstream from that manifest in electromagnetism. You know, perhaps atoms would behave differently if there's some constant electromagnetic field in the universe pointing in some direction. Then you get different results depending on how your laboratory is conveyed with respect to that. So the next slide is a slide we can skip over. Here's the math. I'm going to give give your audience a couple of seconds just to verify that equation is right. So yep, okay, yeah, it looks right. The J phi term, yeah.
I'm not. I think I don't know, man. This term here, I got a problem with that one.
All right, well, we'll work on that. So now going down to how you would test it, the next slide shows Jim Simons, who is the patron of the Simons Observatory, the Simons Array, and many other things in the world of pure basic science. And what Sean did with his colleagues in 1990 is add a term to the Lagrangian. It's not super important. The key thing is that he added a specific direction in space, and he added that as a 4 vector, as a vector with time and spatial components, so that there was a direction pointing in space that was different than every other direction. And the reason we don't see any effects of that is that we don't have photons that have been traveling far enough for this effect to accrue to observational levels. In other words, we can rule this out on Earth. We don't see the polarization of photons of a laser. Say you polarize a laser beam and shoot it down a kilometer to another laser detector. We don't see that rotating unless we put magnetic material in and a magnetic field. That's called Faraday rotation. But instead, we don't see this in the lab, but maybe it's just such a small effect. It takes cosmological distances traversed by photons to accumulate enough of a rotation to be detectable. So in fact, this is the 3rd or 4th time in history it's been detected. The next slide shows a claim made about my experiment, BICEP 1 data, that they detected at greater than 3 sigma this rotation angle, which the authors of the current paper in PRL call beta. I don't know why we can't get our language together. I call it alpha, they call it beta. Some people call it psi. It's not important. It means that photons will change their orientation as they come to the observer. They will rotate their plane of polarization, all in the same sense. And that sort of is singling out the time direction as different from the way that it would depend on a universe that doesn't break this type of symmetry. So this is adding a type of scalar field to the electromagnetic Lagrangian that also produces this effect. So they show the same kind of additional term into electromagnetism. Now, I said this is the 3rd time it's been detected currently, or evidence for it. I should say that the current authors just say evidence for, or perhaps they say extracting it from, but they don't go so far as to say that even with 99+% confidence that they've detected it. So next slide, Tony.
Well, hang on. So in order to see this polarization shift that you're talking about, photons have to be traveling on the scale of the universe.
Yes, or at least at the scale of galaxies, far away radio galaxies. That's right.
So some of them maybe Z
megaparsecs, yes,
or something.
Exactly.
Okay, all
high
right.
Redshift, yeah.
So this would be in effect if the universe has a direction and violates the Lorentz propositions or whatever with that math we saw. Mm-hmm. Then this would manifest itself as a shift in polarization of photons over the course of a cosmic distance scale of the universe.
Correct.
And of the observable universe. And this is called cosmic birefringence.
Yes.
And birefringence, you better say us what that is, what that word is.
Yeah, so birefringence is a property of certain crystals, in particular quartz or calcite crystals. One type is known as Icelandic spar. I have some of that in my house somewhere. I could run and go get it.
Calcite is birefringent?
Calcite is birefringent. Quartz, a specific crystal structure of quartz called Z-cut quartz. And we make devices that are polarization modulators out of known birefringent material, like quartz. Sapphire is birefringent, etc., which just means that as as polarized light travels through this crystal, through this material, the plane of linear polarization can rotate. And it can do so independent of electromagnetic frequency. And it has no effect on unpolarized light. There are other effects that can cause depolarization and other effects. We won't get into that. But the basic conjecture is that the universe does not possess this property. In other words, the vacuum of space does not produce this property. But effectively, if it did, it would mean that light of one polarization state travels slower than the speed of light. And the other,
and that would be a property of space-time itself, then, wouldn't it?
the vacuum. Well,
space-time would be birefringent.
Yes, it would lead to
cosmic birefringence.
That's right, and it would be true on Earth too. It would just be so small that we can't detect it because the amount of rotation depends on how far the photons have traveled. You see that blue teal colored line?
It's hard to see, but it is kind of twisting over the distance that it's.
And I could actually make it thick enough that it rotates by 90 degrees. So you can make it, you can increase the amount of rotation or birefringence two ways. One, a stronger amount of this breaking of parity symmetry within the vacuum of electromagnetism, or by having a longer path length. But you can't get a longer path length than going from the photons produced after the immediate effects of the Big Bang, namely the cosmic microwave background or CMB photons. That's the longest path length possible in the universe. It's effectively almost the entirety of the entire universe, 45 billion light years.
That's right. Yeah. So
the next slide shows.
Is this right-handed or left-handed?
So it could be either one. So you could have either one. So that would break parity symmetry, in that the laws of nature don't depend if you're looking at something in a mirror. They seem to be symmetric with respect to that. They're not symmetric with what's called charge parity symmetry violation, but they are symmetric with respect to charge parity and time reversal symmetry. And that's a subject for another day, maybe another claim detection. We'll talk about that. Those are called the discrete symmetries of space-time that all theories of physics have to live up to. So in some sense, this could be used to test the existence of a theory of everything, which is why I'm personally extremely excited about it.
Okay, I don't get that connection, but I guess I don't have to. Okay, here's the New York Times.
Yeah, so if you go back to 1997, you're back. I know you've got stockpiled in your basement, all issues going back to April of 1997.
Are you calling me a hoarder, man? Is that what you're saying? I'm not a hoarder.
You're a prepper, you're a hoarder, whatever.
I am a prepper, but I'm not a hoarder.
So at the bottom, it says, this side up may apply to the universe after all. So that's kind of a tongue-in-cheek way of saying that there is a preferred direction to space. I also pointed out to Sean, I like the fact that the New York Times is time translation invariant, because you still see Newt Gingrich in the New York Times every day, or a couple times a month. You still see Bibi Netanyahu is also there. Slobodan Milosevic and is on there. Anyway, so it's just funny that the more things change. I bet you could find Donald Trump in there somewhere. Certainly Joe Biden was in there somewhere.
Well, there's an argument that the Times kind of made Trump because they loved him in the 80s and 90s. So they kind of built him. Yeah.
So if you look at this slide now, this is getting into a little bit more of the details. So they're showing these two different axes that are perpendicular, and depending on which direction light is traveling from a distant radio galaxy, that will produce a measurable rotation effect that one could potentially observe. And therefore,
in the polarization of the light coming through it. I want to keep saying that so that we know what we're talking about.
Yeah. Okay. So the next slide shows some of the data that Sean had analyzed for his PhD work in that 1990 paper. And it shows just a cartoon of what these radio galaxies look like. Seems to be a preferred orientation between the radio polarization properties and the optical polarized properties. And this just describes a little bit about, if you can measure the spatial geometry, you could measure the angle with respect to polarization. And what Sean showed very soon after, which I thought was amazing feat of scientific integrity. Imagine you've predicted that there is imagine you predict, Tony, for a second, there's a preferred direction in space, but no one believes you, and no one thinks you're right. They think you're smoking something special that you can get in California now. But you believe it with all your heart, and then somebody comes out with data that proves you right, and then you set about to prove them wrong. I mean, I don't know. I saw this.
It is refreshing. I mean,
yeah, I don't think I could do that. That's why he's a hero of mine too. Sean and I differ on some things. We agree on other things. And what's so important is how he had the scientific integrity to look at a signal that could have been, touted and was touted as having this incredible import and proving his paper's conjectures of 7 years earlier. And yet he had the integrity to kind of show that they had made a simple blunder with the way that they assigned what's called the sign convention for polarization. Polarization can't distinguish, unlike this pen. This pen has an obvious, parity difference with the point on one side and the tail on another side. But imagine a piece of spaghetti, which has no symmetry, has perfect symmetry up and down. You can't tell the difference between a piece of spaghetti like this or a piece of, blink, and I'll turn it around. This piece of spaghetti like this are the same thing to astronomers. And what these guys did, the authors of the paper, Nodland and Ralston and Nodland, they arbitrarily made up a convention that basically forced them to get this distribution peaked at 90 degrees, as shown here. And it was really done kind of arbitrarily, capriciously. And Sean discovered that, refuted them in a series of papers, and then this all went away. But it's funny, because it goes from front page of the New York Times to completely forgotten. But we haven't forgotten about it. And as I said, it was claimed from the BICEP 1 data to be existent back in 2009. So that's 11 years ago. And lo and behold, 2020 comes along, and to add to the amazing simulation, as people are saying in the chat room, we have now seeming to believe that our most cherished principles of physics, namely Lorentz violation, may be getting destroyed in this very strange year. So we don't have to talk too much more about this aspect of it. I do want to get to kind of the most important part of it is, in my mind, what separates these authors from other ones is that they have done a very careful job of looking at what are called systematic errors. And those are errors in the instrument, errors that can come from sources that aren't cosmological and mainly mimic and confuse observers. And they've done a good job at treating that. But it was interesting to talk to Sean, explaining, to the audience also how hard it is to calibrate an astronomical instrument.
Yeah.
And why that's so important.
Right. And so I agree that we should probably not we'll let Sean do the description of what he's done and in the interview that you had with him. But this is amazing stuff. And I guess I wonder about why was the Lorentz postulation given that way in the first place? What made everybody think that there wouldn't be a preferred direction to the universe? Why is that the supposition?
Yeah. Well, so going back, I've been reading a lot of Galileo's original books, the dialogue in particular, the dialogue on two world systems, which I always point out had originally had a much fancier and more attractive title that Galileo gave to it, which was on the flux and reflux of tides in the Earth's rivers and ferns. I don't even know what a fern is, but that's what Galileo wanted to call the dialogue on the two world systems. And I think, that really would be impossible not to read such a book. But actually, the Pope essentially forced him to change it to the dialogue, which is good that he did it, because it's a much catchier and much more intriguing title than flux and reflux of tides.
Well, so that's interesting. I did not know that the Pope had input on. He didn't have input on making the format of the book a dialogue. I thought Galileo did that when he wrote it.
Yeah, I'm just saying
in the form of a dialogue, so that he could have this buffoon type person with which to put his arguments against.
That's right, and the buffoon was representing the arguments of the Pope.
That's right.
Which is.
But it was always written as a dialogue, I guess, is my point. It wasn't.
Yes.
Okay. It wasn't
written in
changed by the
Platonic
Pope.
style. And in fact, even after Galileo was imprisoned, he wrote one more book with the same three characters called The Discourse on two new sciences, which were really about mechanics and what we call statics and material science. But we'll get into that some other time. But getting back to the dialogue, Galileo spends an awful lot of time talking about if you drop a cannonball from the mast of a ship, as the ship is sailing at high speed, it will still land at the base of the ship's mast. If you have a bunch of butterflies in a jar and they're floating around in the jar as a boat is sailing, they don't notice that they're moving. And so the relativity of motion, as Galileo first explicated it, is really sacrosanct in physics. And if it did depend on motion, we would have a very strange world. In other words, you got different results. You could tell that you're moving. It would have dramatic implications. That's where the relative and relativity comes from, is that it's impossible to say who's in motion when two objects are moving in inertial frames. So it'd be very difficult to do physics if Lorentz violation took place on a daily basis.
I see, because not only do you have that complication of the preferred direction or the birefringence of space-time, but you've also got the complications of your inertial reference frame. So if you're in one reference frame and I'm in another and we're doing the same experiment, we're going to get different results as a result of the fact that we're in different reference frames, especially with respect to time, we then have to also account for this birefringent effect in the space-time that we're traveling through.
And actually Aristotle, who was not known for doing anything correct in physics, but nevertheless had a lot of interesting conjectures. His model of the Ptolemaic, it came to be called the Ptolemaic universe, that had a violation of Lorentz invariance in that it was assumed that heavier things fell to their centers. In other words, that the Earth was the center of the universe because it's the most important place in the universe, and everything goes down towards the Earth, and as we perceive it, and everything orbits around the Earth, and that's proving that we are the center of the universe. He also thought heavier things fall faster than lighter things, etc. And that's a form of Lorentz invariance that we know not to be true.
Okay. Well, let me get to a couple questions here.
Yeah.
Dan wants to know, are you talking about items falling in a vacuum? I assume you mean when we were doing that the thing about Florida versus California.
Yeah,
it doesn't matter, really.
It could be in a vacuum. So if you take a proton and you put it in orbit around the Earth and you ask, well, how fast does it fall? It would fall at the same rate if you did that test, assuming that it was just falling around orbiting the sun or something. It would fall towards the sun. But if you had a charged magnetic field throughout the universe, it would fall in a different velocity depending on whether or not it was perpendicular or parallel to that electromagnetic field. So you could derive your orientation, and that would break Lorentz invariance. It would add a preferred vector field to the universe that we don't observe to be the case.
All right, and Sol Tube. So this means we can find the center of the universe / space. We can send a satellite there at 99.9999999% of the speed of light with a message. Yo, God, are you there? Why the absent parenthood and polemic? All right, let's go to the first part of that. So is this somehow pointing us towards a center of something?
Well, if it were true,
I don't think so.
Then yeah. So if it were true, it wouldn't necessarily imply a center. It could imply a direction. So if you have multiple directions, let's say you had one, the universe doesn't have to just have one direction. It could have many different, it could have a tensor, it could have all sorts of different phenomena that would break symmetry such that, crystals would form differently depending on the orientation of the axis. And so effectively, it's often said that while the cosmic microwave background provides a universal reference frame, but what we're saying is not that there's impossible to have a reference frame or even a reference frame. I mean, my GPS will get me to Florida just fine, even though, the Earth is a gravitational field. I'm not technically in an inertial reference frame. And what relativity says is that you can have a whole bunch of local reference frames, local inertial reference frames, but there's no global one that connects all of them together such that all observers will agree that so-and-so is motion at constant velocity. That's really important, actually. That is. Yes, it is.
There is no spot upon which everything is at rest.
Yes.
Right. There's. Okay.
That's right. And so there's no center of the universe, right? If there were, there would actually be, as this listener is saying, there could be an actual, claim that there's so-and-so is at the center of the universe, because that's where these symmetries properties would vanish at the origin. I mean, it would be symmetric only in one special location. That location could consider itself the center of the universe. But of course, we don't think that's true, at least until these results are confirmed.
It's really hard to imagine something like the Big Bang and an expanding universe and not imagine, because it's just so common sense to us anyway, that there is a center somewhere. And I get that bias. I want it to be true too. It just makes visualizing the whole Big Bang thing easier. The thing is, though, it betrays just what the Big Bang was. The Big Bang wasn't an explosion that happened in a spot and then it expanded outward. It happened nowhere and then created from it an expanse of space-time. It created the map that we live on, the three-dimensional space that we live in. And if you go to any spot within that expanding frame, there's no center to it. You can look in all directions and you're gonna not find any closer to an edge than any other spot. And don't feel bad if you can't visualize it, because it's very non-intuitive. I can't visualize it. I'll just say it flat out. So
yeah, well, I think how magical it is that we're talking about things that occur in 4 dimensions. We're talking about properties of space, time, not just space and not just time. And it's pretty amazing that we can visualize it at all. If you think about it, our eyeballs have retinas that are essentially 2-dimensional structures, right? So our retina is a film on the back of our eyeballs. And from 2 of those, we synthesize perspective, almost like a 3-dimensional, but we don't see inside of something, right? So we're not really seeing the third dimension. And now we're talking about a 4th dimension. So yes, it's extremely complex to visualize these types of phenomena. And no one should really feel, it's said that no one can visualize it. There are ways to think about it. I'm going to be doing a special 4-part video series on my channel when I get the time, on a book called Flatland, which is really the best science fiction, science fantasy book that I ever read as a young kid. I started reading it when I was 12, finished reading it when I was 49, which is hard to believe because it's only 89 pages long. But it's a
pamphlet.
I got a little bogged down for a couple of things happened to me along the way there, but it's a delightful book. I've read an illustrated version of it, and it talks about how a planar creature, a creature living in 2 dimensions named A square, could conceptualize the 3rd dimension as when he encounters a mysterious creature called a sphere who comes into Flatland and also causes a lot of trouble for this character. I won't spoil it, but it's an amazing book, and I hope to give my perspectives on it and also couple it to these new theories of geometric physics promulgated by my friend Eric Weinstein.
Good. Well, definitely we'll check that out as well. Okay, I want to get to some comments. Frederick Rhodes, sounds like Birkeland currents. You know what those are? I don't.
Nope. I have no idea what those are. Someone's asking, I think Andrew Planet is asking.
Andrew, hey.
Yeah. Are we talking about ferns like biological? No, fern to Galileo is a river delta. And I think somebody else said that in the chat. So no, a fern, Galileo meant some kind of river structure that was called a fern.
Right. And here's a question from Neil. Brian, could this indicate Dr. Turok's universe plus antiverse concept? Maybe the antiverse has the opposite preferred direction.
Yeah, it's interesting. There are works of physics, and I talked to Sean about this, how this could be coupled into, theories of gravity, theories of everything. And in fact, the theory of everything presupposes that there is one unified law of nature, of physics. And that we already know that electricity and magnetism are unified. We know that heat and thermodynamics are unified. We know that the weak force is unified with the electromagnetic force. We suspect that the strong force is unified with the weak force and the electromagnetic force. And then the supposition is, well, the theory of everything should unify all those forces and gravity. And I said, what would be the implication of such a unification? Would it be manifest in a type of Lorentz symmetry violation or parity symmetry violation? And we talked about this. There are Neil Turok and Paul Steinhardt and others have different concepts for the universe, the antiverse. But there's also consequences that could emerge, such as not only photons being chiral or handed, but also gravitational waves being chiral or handed, so that a left-handed or vertically polarized gravitational wave, if you like, would travel slower than a horizontally polarized gravitational wave. So yes, these are all things that could have a bearing on the time direction asymmetry, as well as directional dependence in the three spatial dimensions of space-time.
Let's see. I want to get to a couple more. So Frederick really wants to get God in here. The positive and negative pole directions are controlled by the governance of direct. Don't know what that means.
No, I don't know either. Yeah. Dallas Brown is saying we're very smart. I like that.
Hang on, you're getting ahead of me. Oh, okay. I won't put that one.
I'm on my channel. I don't know if you're.
It's on yours. Okay, I'm putting up the questions on the thing. So Andrew Planet has another question. Does the fact that this universe has a measurable lifespan since the Big Bang imply a trajectory? See, that's what I mean, right? You start going there with this Big Bang happening, and then there's an expanding universe. The thing is, the Big Bang happened in nothing, right? There was nothing upon which it happened. So there's no like direction in nothing. So it's tough, man. But anyway, what do you say to Andrew?
So what's the exact question, Tony? Sorry.
What does this fact? Can you see what I'm putting up on the screen?
I can. Yes. Okay. Does the fact that it has a measurable lifespan imply a trajectory? So trajectory has this connotation of direction in space. I don't think that's effectively, a precise question, in that the universe isn't moving through something if it's all there is. Now, if there happens to be a multiverse and there's other, there are other phenomena, there are other things in the universe than we can see, then yes, it could be, that we are moving with respect to another universe in the time domain, but in a larger spatial context called the multiverse.
All right, this has got Andrew's curiosity up, so he's got another one. Does the fact that this universe has a certain specific age mean that it is relatively finite but just immensely big?
It could be immensely big, and it does have a finite age, we think, but that doesn't mean it had a single Big Bang, that it was created in a singular universe. It could be, as Turok and others suspect, it could be a type of cyclical universe that comes into and out of existence and bounces into and out of existence, if you will. So there are many different possibilities that could occur. And I think what's interesting is that now, especially with Sir Roger Penrose getting, his attention due detention. Don't get me in trouble, Tony. But the actual conformal cyclic cosmology that he prefers is sort of an endless cycle of what he calls eons that would go on to eternity in both space and time in a certain sense.
Yeah. Okay, a couple more things here. Hey, Christians, good to see you, man. Thanks for showing up. Let's see. One more. Let's see. Should have been called The Big Expansion, not The Big Bang. Very true. And Andrew Planeticus is commenting, perhaps we really need technology to see and understand other dimensions, unlike animals. That's a good comment. Let's see. Frederick Rose, eyes and our other senses detect different types of the electromagnetic spectrum. I don't know about other senses. Only our eyes detect the E and M spectrum. I guess unless heat. Well, no, I guess your fingers detect infrared pretty well, don't they? It's like, yow! Okay, so I guess that's true.
Ooh, Hans just kicked in $20. Well, I don't know. What's DKK? What is that? Is that North Korean yuan or
I think Hans is from Denmark, I think. I'm not sure.
Okay. So Denmark kroners. Thank you.
I think, yes. Thank you, by the way, Hans. He always supports, and he's always really generous with that. So thank you, man. It means a lot.
So we think it could be it could be a couple pennies. I don't know.
Yeah. So John Suffel is, in the beginning was nothing, and then it went splat. And the biggest mystery is why it freaking bothered in the first place. Very good. Yes. And Hans is asking the eternal question: When do the U.S. go back to normal time? That's a great question. I think this weekend we have a lot of things going on. We have
unless you're in
Halloween
Arizona,
happening.
unless you're in Arizona, right? You never.
Oh, that's
change.
right. And there's another state too, I forget, that doesn't bother with it. But yes, this weekend we have Halloween, we have a full moon, and we fall back on our time. So you can be sure the United States may not be around on Monday. It may not survive that
Tuesday
catastrophe. All of which, and then we get to worry about an election in 2 days. So yes, the world is in fact
the
coming
universe.
to an end.
The universe is all screwed up.
Yes. Okay. So all right. It looks like that's most of our comments that
I have a couple
through.
here. Let me just see. Is there a cosmic
Go
starting point? Could this mean there's a cosmic starting point, potentially a white hole? Yeah, I actually talked today with an astronomer named Paul Sutter, who's written a book, How to Die in Space. He runs a competitor channel to my channel and to Tony's channel named Ask a Spaceman. He's a phenomenal.
I don't compete. You guys win.
You guys, yeah. That's what you say when you don't have to compete, Tony.
No, I don't. I don't want to compete.
I see
really
Chris.
don't.
Chris is here from Launchpad Astronomy. He also doesn't. He's at that exalted Michael Jordan level.
Oh yeah.
I want to say that we're going to have a series, or actually not a series. I'm going to be doing a bunch more live streams. So part of the awesome benefit of having a YouTube channel and a podcast, but also being active in science research, is that I'm getting to talk to these people like Sean Carroll, like Max Tegmarks, and so forth, Eric Weinsteins. What we want to do is leverage.
Yeah, you know
that.
all the cool kids. Yeah, definitely.
Well, I'm getting them all together on November 10th at 9 p.m. Eastern time. We are going to do another live virtual stargazing. This time with Adam Rees, Nobel Prize winner Adam Rees, and with Wendy Friedman, who's one of the most brilliant scientists in the world, Professor Sarah Seeger of MIT, Professor Jana Levin, who's coming out with a book.
I got to talk to her in a couple of hangouts. Sarah's awesome.
Yeah, Sarah's amazing. And Jana Levin has a new book coming out on November 10th. So I'm going to do 2 live streams with Jana Levin. You got to tune in for that. She's just blowing up. She's one of the coolest people in the world. She was on the Tim Ferriss podcast over the summer. She's having a movie made about one of her books by The Moth. And so we're going to do live streaming like we did over the summer with Wyoming Stargazing Association with a 20-inch, half-meter diameter telescope looking at the Hubble Space Telescope's greatest hits. Because as Tony knows, it's the 30th anniversary of Hubble. I just wrote an essay on my YouTube channel called The Greatest Debate, but not about the Biden-Trump debate, but about the great debate between Curtis and Shapley that hoped to decide the origin and the size of the universe and ended up doing neither for several years until, like hanging chads in Florida, it was eventually decided by Edwin Hubble, whose telescope has its namesake telescope has its anniversary. And the last thing we're hoping to observe is a passage by the International Space Station, because you may know it's also the 20th anniversary of the launch of the International Space Station. So
God, I feel old.
We are doing a lot of deep astronomical observations, live astronomy and deep astronomy on the Dr. Brian Keating YouTube channel. So look for that with authors, Nobel Prize winners, pundits, my friend David Spergel. And that'll be live looking at some of the Hubble telescope's greatest hits. And maybe, just maybe, I'm going to try to arrange a flyby by the ISS, captained by one of my former guests.
You're going to arrange a flyby.
I am. I'm actually going to do that. And it's going to be lit up. Deep astronomy lives here.
Ooh, I like that.
So thank you all so much. Please do subscribe to my channel. I'm trying to grow like my friend Chris, my friend Tony. You guys are really inspirations to me. And I've benefited so much from your generosity and from your graciousness. The two of you guys really always help my channel so much. Tony, I want to thank you so much. Sean Carroll, I want to thank him as well for his time. Look forward to, I've got 3 more Nobel Prize winners coming up live in the next few weeks. So please stay tuned.
Yeah, the link to the discussion that Brian had with Sean is in the description box of this hangout, and also subscribe to his channel and do all those fun things because it is really good content, and I wish I knew the people he knew. I do, because Brian, the reason I get to see and sort of live vicariously through you and talk about and get access to these people through you. So it's really great. Thank you for taking time out for being with us. And I'm going to go ahead and I guess I'll stop the stream here.
Thank you, guys.
I don't know I don't know if I'm going to be streaming tonight on Clear Skies Network or not. I'm not prepared. Usually I stream at 9 o'clock on Thursday evenings Eastern time. I may or may not get my stuff together in time. If I am, I will see you there on Clear Skies Network on Twitch. Otherwise, I will be back look for a Space Junk podcast episode. We have new stuff coming out from OPT, which you guys will want to learn about. And I'm actually going to start making some podcast changes here on Deep Astronomy as well. So look for all of these things. And don't forget, Alexa.
You're going to shave? You're going to shave?
Alexa. No, I'm not going to shave. No. But this is it. This is my beard. That's the best I can do.
Alexa, order razor blades for Tony.
Order razor blades. Say, Alexa, play Space Fan News.
Razor blade refill.
Oh, I'm gonna order me some, are you? All right, guys. Thank you all. On behalf of Brian Keating, my name is Tony Darnell. Thank you all so much for watching. And as always, keep looking up.